In this video, we'll demonstrate how to define a plane frame model. We can see the end result on the screen. Double-click the strap icon on your desktop to open Strap. On the screen, we'll see a model list. This model list includes all models in our working directory. In order to create a new model, we can either go to File, New Model, or use the shortcut in our toolbar. Let's enter a title for our new model. Let's call it Frame in our case. On the next screen, we can determine the units of our model and choose the model type. In our case, plane frame. The next step will be to choose a method to create our model. The first option, Model Wizard, is a predefined library of standard structure types. The second option, Grid Lines, will create orthogonal grid lines as a basis of our new model. Only nodes are defined in this option. For the third option, User Defined, the program will display a blank sheet. Let's choose User Defined. We can see our global coordinate system on the bottom right of the screen. Since we are working on a plane frame model, we are working in 2 dimensions only, x1 and x2. The main menu of the Geometry Definition module is located on the bottom right of the screen. The submenu for every selection in the main menu is located just above it. For any model, we'll need to define nodes. Every element in our structure, such as a slab, a wall, a beam, or a column, will be connected to nodes. Let's start our node definition by clicking Nodes in our main menu and a single node in our submenu. Pay attention that while we move our cursor across the screen, our coordinate toolbar is constantly changing. In order to define a node, we can move our cursor to the desired coordinates. Let's say we want our node on the 0, 0 coordinates. Left-click on the mouse will create a node. Another option is to manually enter the coordinates in the Coordinates toolbar. We can either move to the toolbar with the cursor, or by pressing the F6 key will move us automatically to the Coordinates toolbar. Let's define node number 2 with our Coordinate toolbar. The x1 coordinate of node number 2 is 8 meters, and the x2 coordinate is 0. The Tab key will allow us to move across the toolbar until we get to the green V icon. Pressing Enter will end Node 2 definition. Next, let's define all of our nodes. Node number 3 coordinates are x1 8 meters and x2 4 meters. Node number 4 coordinates are x1 equals 0, x2 4 meters. Node number 5 coordinates are x1 11 meters, x2 4 meters. On the right side of the screen, we can see that even if we define a single node, we have many options. One of them is the same as an existing node. The shortcut for this option is the F8 key. Once we choose this option, the program will allow us to choose an existing node as a reference and define a node relative to the node we just chose. For example, we can see the coordinates of the node we just chose. x1 equals 8 meters and x2 equals 4 meters. By using the arrows in my keyboard, I'll move 1.5 meters higher. Pay attention. The step measurement of the cursor can be found on the bottom right of the screen. We can modify it by entering a value or use the F3 key to increase or the F4 key to decrease the step size. Let's decrease the step size to 0.1. Next, let's press the F8 key for selecting a reference node and move 1.6 meters to the left of our reference node. See in the coordinate toolbar, dx1 equals minus 1.6. dx1 will represent the relative distance in the x1 axis from our reference node. In our coordinate toolbar, x1 and x2 represent the values in the global axis, and dx1, dx2 are relative to the reference node. In order to finish our node definition, we can either go to End Selection or click in again our last selection. For example, let's click the last node we defined. We can see we've ended our node definition. By clicking the Zoom Full Drawing icon, we'll have our full drawing on the screen. Now let's move to beam definition. We'll click Beams in our main menu and Define in the submenu. On the bottom left of the screen, we can see the beam number and the property of the beam to be assigned to it. The property includes a section and a material. Property number 1 will be the default when defining beams. Let's click on a node at the beam start and another click on a node at the beam end. We will define the columns from the bottom upward and the beams from left to right. We will maintain this order because of the local axis of the beams. The local axis will be defined according to the start-end definition of the beams. The x1 local axis is parallel to the axial axis of the beam. Its direction will be defined from our start-end points of the beams. The long horizontal beam we've defined have to be divided to 3 beams to allow the connection with the beams that intersect with it. If Split at Intermediate node is checked when we define the beams, the program will automatically split the beams. Now let's define the beam's properties. The question mark to the left of property number 1 indicates the beams with property number 1 were defined, but the property itself wasn't defined. We'll make sure property number 1 is highlighted in blue, then click Define Revise in order to define it. In our case, let's choose a section from the steel table. We'll choose IPE 300. We can see that the material is steel and the property name is the IPE 300. Now let's define property number 2. We'll choose IPE 400 from the steel table. For property number 3, we'll choose an RHS section, 100 by 100 by 5. Clicking the Assign button will allow us to assign properties to beams. Let's assign property number 2 to our horizontal beam. And property number 3 for our diagonal beams. We can display the section name to check our property assignments. Next, we will define restraints. Let's define fixed restraints for the 2 bottom nodes. We can select the nodes individually or by a window. We don't want our diagonal beams to be fixed to our orthogonal beams. So we'll change the end conditions by clicking the Release option in the Beam submenu and release only the moment at both ends of the beams. Our model geometry is done, but before we are going to loads, we would like to focus on our fully customizable icon toolbar in the geometry module. All of the toolbar icons are shortcuts for the options available on the top main menu. For example, the first icon, Zoom Create a Window, is also available in the Zoom main menu. This option will allow us to create a magnified window The next icon, Full Drawing, as we saw earlier on, will fit our model to full screen. By the way, the mouse wheel operates as a dynamic zoom in and out. Pressing the wheel and dragging it across the screen will move our view, and double-clicking the mouse wheel will give us full drawing zoom. The next icon we'll examine in our toolbar is Nodes Numbering. Clicking this icon will show us all node numbers in our model. The next icon, Beam Numbering, will do the same for the beams. Property Numbers will display the property numbers in our model, and Property by Color will give us only the colors of different properties. Restraints display will toggle the display of the restraints. The next icon will display the section orientation. And the icon right next to it will display the section name. The next icon, Display Data for node beams or elements, will be very useful in a complex model with many nodes, beams, or elements. Let's display the data for node number 7. We can see its coordinates, the beams that are attached to it. Next, if we'll select node number 6, the program will display the distance from node number 7 and the relative coordinates. We can also get information on beams. JA will represent the node at the start of the beam, 4 in our case. JB will represent the node at the beam end, 7 in our case, the property assigned to the beam, and its length. To end our selection, either right-click the mouse and select Cancel, or press the Escape key on your keyboard. Another useful display option is the Display Local Axis. Let's display X1 and X2 local axis. We can see that X1 is the axial axis of the beam and X2 is perpendicular to it. We can also create dimension lines. Go to Draw, Dimension Lines. Let's choose an X2 direction and click 2 nodes. Pay attention to the prompt line in the bottom left of the screen. The program asks us to point out the dimension line location. Another option to display data is through tables. In output, there are many options to display different data in tables. Let's select Display Properties. We can see the data table for all properties in our model. By selecting Display Beams, we can see the JA and the JB start-end nodes of a beam, its releases, its length, its property number, and the material number. Okay, let's move to the Loads module. We will create a new load case, name it Design, and choose Joint Load for the load type. Joint loads can be defined only on a node. Clicking Define will allow us to insert the load value and its direction relative to the global coordinate system. Let's define 5 tons in the -x2 direction. Load units are available at the top of the screen. Let's end the load case and solve the model. Every time we solve a model, the program will ask us if to save the stiffness matrix it calculates or not. Usually, in the simple models, there is no need to save the solution matrix. After solving the model, we are automatically prompted to the Result module. All graphic results can be found in Draw Results. We can choose the display type. In our example, let's choose Beam Result Diagram. Next is the result type. For our plane frame model, M3 will be the moment around the X3 axis. X3 axis in our case is perpendicular to the screen. V2 will display the shear force in the screen plane. We can also see the axial forces. Let's display the M3 results. We can modify our selection at the bottom of the screen. Let's choose axial forces. Positive result will represent compression, and negative result will represent tension. We can also display displacements. The values displayed on the screen are already multiplied by 10 in the power of 1, and the displacement units are also available. So 136 on our screen will represent 13.6 millimeters of displacements. Also available are the reactions in our restraints. We can also display results in tables by clicking Display Table. Let's choose Support Reactions and the load case. We can see the known numbers, the forces in X1 and in X2. X6 will represent moment around the X3 global axis. The total line represent the sum of reactions in every direction. We can see equilibrium with our external force of 5 tons in the x2 direction. That's it for this video. Thank you for watching.